Welcome to the Approach to ABGs Part 11, the anion gap. We're going to explain what the definition of an anion gap is and what causes it and what the processes are that create an anion gap. So anions are negatively charged ions and cations are positively charged ions. And I'm positive that you are not electrically charged. We're not running around shooting electrical static charges out of our fingers all the time. And this is because we are electrically neutral. Our cations balance or equal the anions. So we have a net charge of 0. If we look at all of the cations, which are the positive ones, and the anions, which are the negatively charged ones, this table shows the most common or the ones in the highest concentration. And we're going to actually ignore the bottom 3 because mag phosphate and calcium, they all exist in fairly low concentrations in the blood. They won't have a big impact on the math, and because we're pretty lazy when we can afford to be, we're going to leave them out. So they're not going to be included in the equations. So the anion gap equation says that the cations minus your anions is predicted to be 0. That is, if you're not walking around with some electrical charge. So sodium and potassium minus chloride and bicarb. Those are the most common ones. But we can even reduce this a little bit, and we can simplify by removing the potassium, because we know potassium usually sits around 4 and might be up a little bit or down a little bit, but it's pretty consistent. And for simplicity, we're going to leave it out. And when we do leave it out, standard values of sodium chloride bicarb, we end up with a normal anion gap of 12. Not 0. So this is a little bit surprising because we are electrically neutral. We were predicting that the difference between these two would be 0, and it appears that there are not enough anions. We're missing some anions in the math, and this is what the anion gap is. So let's explore where that's coming from. What are these missing negative charges? They're not tiny ions. In fact, they are large charged molecules. And the most important one is albumin. There are others, such as antibody proteins and other proteins, other large molecules. And we're just acknowledging these. We're not going to include them in the math, but we are going to take a closer look at albumin. And a normal albumin level is about 40 grams per liter, and albumin has a 1/4 negative charge for each gram per liter. So what does this mean? Well, it means it's inconvenient because we have to do some extra math and we have to divide it by 4. But basically, when you have a normal albumin level of 40 grams, it contributes about a -10 charge to the equation. So let's take a look and see what that looks like. So this is your anion gap equation with albumin. And you can see that it doesn't come out to exactly 0, but we're pretty close. And remember, we've rounded off, we've dropped some of the cations and anions. And so if we were to do the math with albumin, we would come out pretty close to 0 at a value of 2. So we're just going to say we accept that. That's close enough for now. And the trade-off is that we can have a pretty simple equation to deal with. And that simple equation is sodium minus chloride and bicarb equals 12. This is a normal anion gap value. It assumes that you have a normal albumin level, and we're ignoring all the small cation and anion values just to make our lives easier. And you need to memorize this equation and memorize the value of 12. So let's talk about how abnormal anion gap, metabolic acidosis, can be created. And it's created when a new acid shows up in the blood. Either your body created it or it got ingested for some reason. And when this new acid is dissolved in solution, dissolved in your blood, it dissociates into a hydrogen ion, which is what contributes to acidity, and it has a negatively charged molecule, which is the salt of the acid. Now, we focused a lot on this acid-base equation looking at when bicarb or carbon dioxide goes up or down. And we're going to do something a little bit different here. We're going to primarily manipulate the hydrogen ion concentration. So if you add a new acid to the blood, the first thing that changes is that the hydrogen ion concentration is going to go up. So right away you know you've got a new acid or worsening acid. Shifting chemistry tells us the equation is going to shift to the right. This is going to consume and lower the bicarb concentration. So when you have the addition of a new acid, your bicarb is going to go down. Now, morphing from the acid-base equation, we're now going to take a look at the anion gap equation. And remember, we've got this new negatively charged molecule, which is an anion, and we've got our existing anion gap equation, and we can see right away from the previous process that the bicarb is going to be reduced. When the bicarb is reduced and everything else stays the same, the anion gap will go up because we have reduced the total number of negative charges, so we've made the difference bigger. And the reason why this happens is because we've got an invisible acid that is showing up, but it doesn't get calculated in the equation. So it's not like we've created additional electrical charge. Everything still remains the same charge, but now we've got an increased gap between the measured positive, which is sodium, and the measured negatives, which is only the chloride and the bicarb. So this is what causes the anion gap to be abnormally increased. Why do we care about the anion gap? Well, sometimes your body creates new acids. These new acids cause the bicarb to be reduced. This creates a metabolic acidosis, and these new acids are not included in the anion gap equation. So it's like there's a footprint. The anion gap is like a footprint of a metabolic acidosis. And a super important rule: if the anion gap is increased, and that means greater than 12, then there is always a metabolic acidosis process happening. And in a few podcasts into the future, we're going to show you how you can use the anion gap to determine if you have multiple metabolic processes.